Lecture problem 4. A 10.0 kilogram box starts from rest at the top of an incline and travels down a 4.00 meter long inclined plane. The incline makes an angle of 37.0 degrees with the horizontal. The velocity of the box at the bottom of the incline is 5.00 meters per second. Determine the work done by friction. The first thing that we usually do to make these questions simple is to use a free body diagram. The box that is moving down the incline is under three forces. The mg is that one that is pointing straight down. The normal force is perpendicular to the surface of contact. This is known as Fn. And finally, the kinetic friction force, which acts up the incline in the opposite direction of motion. This is known as Fk. There are two ways to solve this question. One of them is long and requires you to use the dynamics of Newton's laws and kinematics together. The other simple way is to use the energy tools. In order to find the simplest energy tool that can be used, let's evaluate the work done by the non-conservative forces. Notice that there are two non-conservative forces. The normal force is 1, but the normal force does 0 work because the normal force is perpendicular to the displacement, which is parallel to the incline. Write down here that the work done by the normal force is equal to 0. The other non-conservative force that is acting on the system is the friction force, but the friction force does not do 0 work. As a result, the conclusion is the work done by non-conservative forces does not equal to 0. In this case, the two possible equations that can be used are the following. The work done by the net force equals to the change in kinetic energy, or the work done by the non-conservative forces equal the change in kinetic energy plus the change in potential energy. The second equation is the best in my opinion because it takes care of the work done by the conservative forces and places that energy in the change in potential energy quantity. Now let's detail this equation a little bit more. The work done by the non-conservative forces include the work done by the friction, which is kinetic friction, plus the work done by the normal force. This is going to equal Ke final minus Ke initial plus Pe final minus Pe initial. As I said earlier, the work done by the normal force is equal to 0, and the only quantity left on the left-hand side of this equation is the work done by the friction force, which is what we are trying to solve for. Notice on the right-hand side of this equation that the initial kinetic energy is equal to 0 because the object starts from rest. As far as the potential energy, I'm going to set up the reference height of measurement to be the bottom of the incline. Therefore, the potential energy final is going to equal 0. This equation now is simplified as follows. The work done by the kinetic friction force equals the kinetic energy final, which equals to 1/2 mv final squared. Notice that this part of the equation can be easily solved for because the final speed is given to us. And once the speed is given to us, the best approach is always to use either the work done by the net force or the work done by the non-conservative forces, minus the 0 that comes from the kinetic energy initial, plus the 0 here that comes from the potential energy final, minus the potential energy initial, which equals mgh initial. The only quantity that is left for us to evaluate now is the height initial, which is this point here where the mass started to move. In order to be able to evaluate that height, you need to use the trigonometry of this right triangle, where the sine of the angle 37 equals the opposite, which is the height initial, divided by the hypotenuse, which is the distance d. Notice that the HI now can be expressed in the following form, d sine 37. Now let's substitute this quantity in our work equation. The work done by the friction force equal 1/2 mv final squared minus mg h initial. The h initial is the d sine 37. Solving for the work done by the friction force Fk, we obtain negative 111 joules.